Welcome back to our next lesson into our atoms, molecules, and stoichiometry unit. Today we are looking at stoichiometry and calculations involving reacting masses and volumes, where our lesson objective is to balance equations and perform calculations using the mole concept and stoichiometric relationships, and to understand the concept of a titration. Just below are the learning outcomes that we'll be addressing from the Cambridge curriculum. So stoichiometry is a very useful tool. It's very useful because given just one bit of information in a balanced chemical equation, you can work out essentially any other bit of information in that chemical equation. This is really useful for working out amounts if you need to synthesize something, or to work out concentrations if you've got unknown concentrations. It's a very, very useful tool that chemists can use for a whole number of things. And it's all based on the idea of balanced chemical equations. And underpinning balanced chemical equations is the law of conservation of mass. The law of conservation of mass states that matter can't be created and matter can't be destroyed. It's just a rearrangement of how that matter is bonded to one another. So what that means is that the number of atoms that we start with in a chemical reaction has to be the exact same number as the number of atoms that we finish with in a chemical reaction. You can't create or destroy them in any form. Therefore, chemical equations must be balanced, where the number of atoms in the reactants must equal the number of atoms in the products. So let's consider a balanced chemical equation and really try to underpin what it's telling us. In a chemical equation, you have reactants. So let's consider iron reacting with oxygen, classic Rust equation, to form iron oxide. So what this is saying is that these two things are reacting to form that thing. But we've got to make sure that the conservation of mass is being conformed to. So over here we have 2 irons and 3 oxygens, but over here we have just 1 iron and 2 oxygens. So let's just recap very quickly how we balance our chemical equations. We've got to make sure that the number of atoms on both sides are equal. So let's look at the oxygen. We have 3 oxygens over here, 2 oxygens over there. Now we can't change these small numbers because these small numbers represent the ratio of atoms within a particular compound or within a particular molecule. So all you can change is how many of these compounds or molecules or elements there are by changing the coefficient. So if we want to get these two to balance, we've got to find a common multiple. They have a common multiple in 6. If we put a 2 there and a 3 there, 3 times 2 is 6, 2 times 3 is 6. So the amount of oxygens that we end up with are the same as the amount of oxygens that we started with. But now our ions aren't balanced, so we've got to go 2 times 2 is 4. So we have a 4, change the coefficient. We can't change any of the subscript numbers. So what this is telling us is essentially a ratio of products to reactants. It's saying, in order for this reaction to occur, you need 4 amounts of iron for every 3 amounts of oxygen gas, and that will make 2 amounts of iron oxide. It's that ratio, and this ratio is what stoichiometry is. So there's our first definition for the day. The ratio of the reactants to products is the stoichiometry of the equation. And like I said, using this ratio, using this stoichiometry, if you're given just a small amount of information about a chemical equation, you can essentially get all the other information about that chemical equation. What do I mean by that? We can use stoichiometric calculations based on that ratio, based on the stoichiometry of the equation, to work out unknown factors. We're going to talk about what this means by going through this example together and these steps. So this example states iron oxide reacts with carbon monoxide to form iron and carbon dioxide. Calculate the mass of iron produced when 798 grams of iron oxide is reduced by excess carbon monoxide. So this highlights why these calculations are useful. Because given one bit of information, the amount of iron oxide, we can work out how much iron we're going to produce. So based on how much reactant we have, we can use that to calculate how much product we would expect to make. So our first step says to write a balanced equation and collate the data that you have. Let's write this balanced equation. Iron oxide reacts with carbon monoxide. So iron oxide is FeO because it is iron 2 oxide, and we discussed these Roman numerals, meaning it's going to make a 2 plus iron. So a 2 plus iron. If we have a 2 plus iron, O always makes 2 minus. We know that because it's in group 6 in the periodic table. This is going to make FeO as a neutral balanced ionic species. Iron oxide reacts with carbon monoxide to form iron and carbon dioxide. We need to make sure that this is a balanced chemical equation. So let's look at what we're given. We got one iron going to one iron, that is balanced. 1 plus 1, we've got 2 oxygens in our reactants and we have 2 oxygen atoms in our products. That is balanced. We have 1 carbon and 1 carbon. So we have a balanced chemical equation here. So the stoichiometry of this equation is telling us that we have a 1 to 1 to 1 to 1 ratio for our reactants and our products. This is the stoichiometry of the chemical equation. So we can then use that to calculate how much product we are going to predict to see based on how much of the reactant we have used. So that's what we do here. We collate the data that we're given to make it nice and clear what we have and what we need to do. So it says that we have 798 grams of iron oxide. So let's collate that here. Mass is equal to 798 grams. And we want to calculate the mass of iron that we would expect to make from this amount of iron oxide. So that's step 1 done. Balanced equation and stoichiometric. Balanced equation and collating the data. The next part of the stoichiometric equation is we calculate the number of moles of what we got. What I mean by that is you calculate the number of moles for the species that you have got the information to do. Because at this moment, there is only one thing that we can calculate the number of moles in, and it's this, because we're given the mass to calculate that. So we got the number of moles of iron oxide is equal to the mass divided by the molar mass. We are given a mass of 798 grams. We can calculate the molar mass by adding up the molar mass for this compound. So iron is 55.845 plus oxygen is 16.00, and that's going to give us the number of moles equaling, if I punch this into my calculator really quickly, 55.845 plus 16, 11.1072 moles. In the last video, we discussed significant figures and rounding, and we said that we don't worry about significant figures till the very, very end of the equation, so we don't do any rounding before that. Otherwise, we can succumb to a rounding error and get inaccurate answers. We do have to include units at every step of the way, but we're not going to round or worry about significant figures just yet. Step 2, nope, that was step 2. Step number 3, determine the mole ratio. The mole ratio tells you the ratio based on the stoichiometry of the equation of 2 species that you want to look at. So I put this as getting the n of what you want in a ratio to the n of what you got. And you can remember it this way, or this is how my chemistry teacher taught me to remember it, which has stuck with me all this time, is what you want's always more important than what you got, because you've already got what you got. So you want what you want. So what you want is on the top, because it's the more important thing. If that helps you remember it, then you can use that. So what we want is what the question is asking us. We want the number of moles of iron. What we got is the number of moles of iron oxide. And we can use the stoichiometry to get that as a ratio. Because for every one of these, we have one of these. So for every mole of that, we need a mole of this. So the mole ratio is 1 to 1. From there, we can determine the number of moles of what we want because we've got that ratio down here. So step number 4 is the number of moles of what you want. And what we want is the number of moles of iron. 1 to 1 is the mole ratio, so the number of moles of iron is going to equal the number of moles of iron oxide. Number of moles of iron oxide we have calculated over here, 11.1072 moles. So the number of moles of iron is equal to 11.1072 mole. Then the very last step is we just convert into what the question is asking us. Always make sure that you go back and read what the question is asking you to convert it to, because even though we got the number of moles of what we want, the question wasn't asking us for the number of moles of what we want, it was asking us for the mass of the iron, not the number of moles of the iron. So that is the last step, is you convert. Step number 5 is to convert. So we get the mass of the iron is going to be equal to the number of moles of the iron times by the molar mass of the iron. Number of moles is equal to 11.1072 times that by the molar mass, running out of room here, 55.845. And I'm going to, now I haven't rounded anything yet, I've still got all my decimal places in the calculator here, so I just times that by 55.845, and that gives me an answer of 620.28 grams. Remember the units. Okay, so we've got our answer here, 620.28 grams. Now we want to consider the significant figures in this answer. So what data are we given? We were given mass over here. We've got 1, 2, 3 significant figures, and we're also given data in the molar masses. We've got 5 significant figures, and we've got 4 significant figures. If we remember back from our previous video, our precision in our answer is limited by the least precise measurement in the question. The least precise measurement in the question is this one. This is 3 significant figures, so we are going to want to give our answer to 3 significant figures. So usually I'll just write it below, but I am running out of space. So we'll go up here, and our answer would be the mass of iron is going to be equal to 1, 2, 3 significant figures. We look at the one next to it, it's going to round down, 620 grams, and then state the amount of significant figures that you have answered your question to. So to recap, step 1, write a balanced chemical equation, collate the data you have, calculate the number of moles for the information that you've got, determine the mole ratio, number of moles of what you want over the number of moles of what you've got. You can then determine the number of moles of what you want because you've got this mole ratio, and you can convert your answer to the units that are required. Now we're going to introduce another concept called the molar gas volume, and this is another useful thing that we can use when doing stoichiometric equations with gases. Avogadro, if we remember old mate Avogadro, he was the one who had his constant where we have 1 mole of a substance containing 6.023 times 10 to the 23 particles of that substance. So Avogadro, smart fella, he also decided that equal volumes of all gases contain the same number of molecules. That's an approximation as long as the pressure is not too high or the temperature is not too low. And these instances, they can behave a bit differently, but outside of these extremes, equal volumes of all gases contain the same number of molecules. What is this volume that they will have the same number of molecules? At room temperature and pressure, RTP, which is 20 degrees Celsius and 1 atmosphere of pressure, 1 mole of any gas will have a volume of 24.0 decimeters cubed. So that means 1 mole of carbon dioxide gas, 1 mole of ammonia gas, 1 mole of ozone gas, 1 mole of any gas that you can think of at this temperature and pressure will take up 24.0 decimeters cubed of volume. So we can have a calculation here, equation here, where volume is equal to the number of moles times by 24. Therefore, the relative volumes of the gases produced will tell us the stoichiometry of the equation. Let's go through 2 worked examples. If you want to pause it and just jump in and have a go, do that now, and then you can check when we go through it together now. So as always, we make it very clear what we're calculating, the volume of carbon dioxide gas. We were just given an equation that said is equal to the number of moles times by 24. But in our question, we aren't given the number of moles, we are given the mass. However, we know we've got this equation that we can do to calculate the number of moles using this mass, getting our molar masses off of the periodic table. So the mass we were given was 50.0 grams. Divide that by the molar mass, getting those values off of the periodic table. 2 lots of oxygens because it's carbon dioxide. Plugging all that into our calculator, we get an answer of 12.01 plus 2 times 16 equals 1.136 mole. So including our units here, but not worrying about rounding or significant figures, I'm keeping this value on my calculator. We're going to plug this over here into this equation, times that by our molar gas constant. This will give us an answer of 27.2665 decimeters cubed. Now we can look at the significant figures. In the question, we are given values with 1, 2, 3 significant figures here. On our periodic table, we had 4 significant figures and 4 significant figures. So our answer is going to be to 3 significant figures, 27 point, that's going to round up, 3 decimeters cubed, 3 significant figures. So based on this idea of the molar gas volume, if all gases at room temperature and pressure will take up 24.0 decimeters cubed, and if we have 1.136 moles of gas, we just multiply that by that constant and we get our answer. That's how we determine the volume of a gas. What about working out this stoichiometry of the equation given relative volumes of gases? Now, because we have this constant where equal volumes of all gases contain the same number of molecules, if we have the volumes of gases reacted and produced, then we can very simply work out the stoichiometry of that equation. So we have this example of propane combusting. If you're playing along at home, as always, pause now and check afterwards. So we have propane reacting with oxygen, combustion reaction, to form carbon dioxide plus water, where we have 100 centimeters cubed propane, we have 500 centimeters cubed of oxygen, 300 centimeters cubed carbon dioxide, and 400, was it? Yeah, 400 centimeters cubed of the water. Now, as I said, because we have this constant here, if we just work out the simplest ratio of these gases, then it's going to tell us the molar equivalence of each of those and consequently the stoichiometry of the equation. So we're just going to divide each of these by the highest common factor, which is going to be 100 in each of these cases. And based on that concept of the molar gas volume, it'll tell us that this is a stoichiometry of 1 to 5 to 3 to 4. You could then use that for subsequent stoichiometry calculations. Another concept that we have to introduce for our stoichiometric calculations is this idea of concentration. Concentration tells you how much of a particular solute is dissolved in a particular solvent. For example, salt in water. If you have lots and lots of salt dissolved in water, you have a high concentration. If you have not very much salt dissolved in water, you have a low concentration, you have a dilute concentration. We can calculate the concentration with this equation here, another one of our very important equations that involves the number of moles. This states that the concentration is equal to the number of moles divided by the volume. So our concentration, therefore, will have units of moles per decimeter cubed. Number of moles is our units of mole, and our volume is our units of decimeters cubed, where 1 decimeter cubed equals a litre. So it tells you how much of one thing is dissolved in a volume of another thing. As with our other ones, we have our equation triangle here that you can use to help you rearrange to make each variable the subject. The concentration is the amount of solute dissolved in a solvent to make 1 decimeter cubed. When 1 mole of a compound is dissolved to make 1 decimeter cubed of solution, the concentration is 1 mole per decimeter cubed. Example, if you're playing along at home, pause and have a go at this one to check with us when we do it now. This says, calculate the concentration of 2 grams of sodium hydroxide dissolved in 250 centimeters cubed of water. As always, we make it very clear what we're calculating. It's asking us for the concentration of sodium hydroxide. Let's finish writing our equation. C is equal to N divided by V. What information are we given? We're given 2 grams of sodium hydroxide and 250 centimeters cubed of water. So as with our last one, we can't just plug the number of moles in, we've got to calculate the number of moles of sodium hydroxide. It's going to be equal to the mass divided by the molar mass. We are given a mass of 2 grams. Molar mass we get from the periodic table. Oh, molar mass of sodium. What's the molar mass of sodium? 22.990 plus oxygen, 16.00, plus hydrogen, 1.008. Plug all of this into our friendly calculator. Talk amongst yourselves. 22.990 plus 16 plus 1.008. That will give us 0.05 mole. Not rounding, not worrying about significant figures till the very end. We can then plug this in here. Number of moles is equal to 0.05 moles. Now, our volume was given in centimeters cubed, not decimeters cubed. We have to convert centimeters cubed to decimeters cubed. Now, a centimeter cubed is a milliliter, decimeters cubed is a liter. One way we can consider conversions is if we have centimeters going to decimeters, we would multiply 1 centimeter is equal to 10 decimeters is equal to 1 centimeter. So if we were going this way, we would multiply this by 10. We would divide this by 10. 1 decimeter is equal to 10 centimeters. But we are in centimeters cubed and decimeters cubed. So we divide by 10 cubed and times by 10 cubed. 10 cubed is equal to 1,000. So to convert between our decimeters cubed and our centimeters cubed, we either times by 1,000 or divide by 1,000. So if we're given 250 centimeters cubed, we have to divide by 1,000 to get 0.250 decimeters cubed. So that is what we plug in here. Go to my calculator, I haven't rounded, it's still stored in here, and I just divide it by 0.250, and that will give us an answer of I'll use my black pen to be consistent, running out of hands, 0.200 mole. Let's look at our significant figures. In the question, we were given information that had 2 significant figures, 5 significant figures, 4 significant figures, and 3 significant figures. So we have to give our answer to 2 significant figures because that is our least precise. So this is the case where we do have to have a 0 after our 2. Even though 0.2 is equal to 0.20, they're the same number, we have to report it to 2 decimal places to show that that is 0.20, not 0.21 or 0.22, because that's the precision of the question. A titration is a very useful analytical tool that we can use to analyze unknown concentrations and determine what the unknown concentration will be. What does this say? Titration is an analytical technique used to determine the concentration of an unknown solution. So you react a solution of a known concentration in the perfect stoichiometric ratio of the reaction. What does the perfect stoichiometric ratio mean? Let's think the example before where we had 4Fe plus 3O2 goes to 2Fe2O3. So the perfect stoichiometric ratio of these two products is 4 to 3. So we put 4 molar equivalents of that for every 3 molar equivalents of that. That's the perfect stoichiometric ratio in this instant. So that's what a titration does, only it does it with 2 solutions. The perfect stoichiometric ratio to make that reaction exactly reacted. So there's no products left, there's no reactants left, there's only product. What you do is you add this thing called the titrant. The titrant is the known solution. You put it from a burette. This here is your burette. So you put your known solution there and you react the perfect ratio with the unknown solution, which is the analyte. So you have your unknown solution here, your known solution there. You react them in the perfect ratio. How do you know the perfect ratio has been achieved? You do it by measuring the pH. The unknown solution will have an indicator, so down here. You can use the change in pH and therefore the color that will be seen, because you'll have an indicator in there, to determine when the reaction is complete. This is called the endpoint of the reaction. So you use the change of color and indicator to show the pH has changed, and that has shown that the perfect stoichiometric ratio has been achieved. You can then use stoichiometry to determine the unknown concentration. Let's do an example of stoichiometry using a titration and using our concentration equation. So this is tying up a fair bit of what we've done today all together. As always, if you're playing along at home, pause now and have a go. 25.0 centimeters cubed of a solution of sodium hydroxide is exactly neutralized by 15.10 centimeters cubed of sulfuric acid of concentration 0.200 moles per decimeter cubed. Calculate the concentration in moles per decimeter cubed of the sodium hydroxide solution. That is a lot of information in that question. So we want to make our calculations very structured and very orderly so that we make it very clear how we're communicating our calculations. So when we're doing stoichiometry equations, we start stoichiometric calculations, we start with a balanced chemical equation. This is an acid base. We have sodium hydroxide plus sulfuric acid, H2SO4, aqueous, aqueous. Acid base, we form a salt, which in this case would be sodium sulfate, and water, H2O, liquid, aqueous. Let's balance it. Conservation of mass, very important. We have 1 sodium going to 2 sodiums. So straight away, we've got to have a 2 there. 2 sodiums going to 2 sodiums. We have 2 oxygens going to 1 oxygen. We have 3 hydrogens going to 2 hydrogens. We have 1 sulfate going to a sulfate. So I'm sort of going to count these as just 1 sulfate as opposed to mixing it up with these oxygens there. So what do we need to do to balance it here? Let's pop a 2 there to make those 2 oxygens the same as those 2 oxygens. Now we have 4 hydrogens. We have 2 plus 2, 4 hydrogens, 1 sulfate. We have a balanced chemical equation. Great. Then we collate the data. What data were we given? We were given a volume of 25.0 centimeters cubed of sodium hydroxide. Volume is equal to 25.0 centimeters cubed. We were given 15.10 centimeters cubed of the sulfuric acid. We were given a concentration of sulfuric acid of 0.200 moles per decimeter cubed. So what this means is that to react these two in the perfect molar ratio, so 2 moles for every 1 mole of that, it took that amount of volume of this, which is our unknown concentration, which is what we want to know, and it took 15.10 centimeters cubed of that sulfuric acid with that concentration. So if we go back to our pictures on the previous slide, we would have our known concentration, the titrant, so we would have our sulfuric acid in there. We would have our sodium hydroxide in there with the unknown concentration, but we do know the volume of it. The volume is very precisely measured out. So we add this little by little by little, and we have an indicator in here. So sodium hydroxide is alkali, sulfuric acid is acidic. So when they've reacted in the perfect stoichiometric ratio, we will end up with a neutral compound, or a neutral solution, I should say more accurately. And we can see that because we're going to have a color change in the indicator to indicate that endpoint. So it's asking us to calculate the concentration in moles per decimeter cubed of the sodium hydroxide solution. One thing we haven't talked about yet is making sure that our units are the correct units for our calculations. Our concentration needs to be in decimeters cubed, but our volumes are in centimeters cubed. So the very first thing we want to do is convert these volumes. So this will be 0.01510 decimeters cubed. This one will be 0.0250 decimeters cubed. Concentration was unknown. Concentration was equal to 0.200 moles per decimeter cubed. All right, after we've done that, we calculate the number of moles of what we got. The number of moles of what we got, what we can calculate is this one here, because we've got a volume and a concentration. So the number of moles of sulfuric acid is going to be equal to C times V. So that's rearranging our concentration. N is going to be equal to C times V. Let me flip back to the whiteboard. Our C is equal to 0.200. We're going to multiply that by 0.01510 because we need to make sure the units are the same. We're going to punch that into our calculator. And we have 0.200 times 0.01510. Lots of zeros. 0.00302 mole, not rounding or doing anything just yet. Then we get the mole ratio. Mole ratio. So the number of moles of what we want over the number of moles of what we got. Because what we want is more important, so it goes on top. What we want is sodium hydroxide. So the number of moles of sodium hydroxide over the number of moles of what we got, which is the sulfuric acid, is equal to a 2-to-1 ratio. So it takes 2 of these to react with 1 of those. From here, I'll put a little line down the middle to avoid it getting too cluttered. We can calculate the number of moles of what we want. And what we want is the sodium hydroxide. And we said down here, the number of moles of sodium hydroxide is going to be twice the number of moles of the sulfuric acid. So we go 2 times by that number there. We've got that number in our calculator. I'll just go times 2. We have 0.00604 moles. That's definitely one I could have done in my head. And then finally, we convert into the units that we want. It asked us for the concentration of sodium hydroxide. So the concentration of sodium hydroxide is equal to N divided by V. We're given the number of moles of 0.00604. Divide that by the volume, 0.0250. That's going to equal 0.0250. 0.2416 moles. They're all my decimal points on the calculation. We're nearly done. The last thing we've got to do is work out what significant figures we need. In our question, we are given 4 significant figures there, 3 significant figures there, and 3 significant figures there. So our answer is going to be 0.246 is going to round it up to 2 moles to 3 significant figures. Whew, so you can see lots and lots of steps are all collating together to make quite, complicated equations, calculations really. Not too complicated, but with so many steps, you can have, it's not too hard to just mess something up here and then that carries all the way through. So that's why you want to make sure your thought process of how you're calculating each step is very clear, so that even if you do a mark wrong up here, they can still see that you're doing the correct method all the way through to get to the answer, and you don't keep getting penalized for wrong marks because you haven't shown, or it's really hard to interpret how you're doing your calculations. That concludes this lesson on stoichiometry and reacting masses and volumes. What have we done? We have looked at how to write and construct balanced equations. We've performed calculations from reacting masses, volumes of gases, and volumes and concentrations of solutions. And we have deduced the stoichiometric relationships from these calculations that we've done. As always, if you want to consolidate your learning, here are some tasks you can do. Start at the bottom, do 1 column at a time, pause that if that is something that you would like to work through. Thanks for your time. I will see you on the next one.